Okay, hello. Welcome to the next part in this little series about PySpice. We're going to be starting off by talking a little about how we can actually use it, giving an example of a voltage divider, and maybe addressing some issues around the syntax, netlist, and then finally we are performing a operational analysis using PySpice. So we've now moved over to Atom. I use Atom as my text editor. I find it's a very nice text editor for Python. We're also going to be using Subsystem for Linux Windows to run our Linux environment, as you can see here. So we'll be using that later. But first of all, I just want to discuss some various aspects when using PySpace or PySpice, or how some of the things that I find are necessary. So I'm not going to bother typing this in, but just be aware that you need to make sure you import NumPy. I'm just importing some of the basic packages here, which we may want to use later down the line. So we have NumPy, matplotlib, we import sys. And then next, to do with PySpice, we actually import PySpice directly. I'll explain why in a second. We can import the PySpice logger. We need to import the PySpice netlist, which allows us to create a circuit. And then we can also then do PySpice.unit import star, and this means that we can use the PySpice units, such as selecting a kilo ohm for a resistor. So that's a sort of a necessary part. Next, we then import the logger. This will then display logging advice about the simulation being run on the command line. So we can import the logger as seen there. We set it up. And then next, I find this is necessary. What I do is I adjust the default simulator used depending on the platform. Now, the default simulator is the shared library. This is something which is used in the Windows when you install the .exe version. We use the shared library. However, when you're on Linux, you want to make sure that you switch over to the NGSpice subprocess. So that's actually needed for Linux, or you can get some errors. I introduced this simple if statement saying, if we're on Linux, then use the NGSpice subprocess. If we're on Windows, then don't do anything, and it will leave it as the shared library which is needed. Okay, so what we're going to do now is we're going to look at a voltage divider. So I'm just going to make a simple voltage divider, and then we're going to use a operating point analysis on it. This is very similar to the example given on the website, which can be found at this link. You can navigate to the examples on the website. I'll probably leave a link in the description for you. So the first thing we're going to want to do is we're going to actually want to create a circuit instance. So to do that, we can name the circuit. I'm going to very unimaginatively name it circuit, and then we call what we imported earlier, which is circuit, and then I'm going to name the circuit voltage divider. So this is, if you've seen a netlist before, this will be the name of the netlist circuit. Next, we're going to add a few components, 3 components to be specific: a voltage source, and then 2 resistors. So we're going to call our circuit, and we're going to add to our circuit a voltage source, and we're going to name the voltage source node input. Sorry, we're going to name the voltage source input, and then what you might consider to be one side of the voltage source is going to be connected to in, the node in, and then the other side is going to be connected to the circuit ground. And then we're going to add it. We're going to specify voltage, and we're going to use 10 volts. and that's how you specify that. Now, I believe there are a few different ways now of specifying the units. This is the one that I've been using since previous versions of PySpice. So what we do to specify it is we use @ and then we do a U to denote a unit, underscore, and then we underscore the unit. So as you might imagine, when we want to add in our resistor, it's quite simply circuit.r, and then we're going to name this resistor just resistor 1. Then we're going to connect one side of the resistor to the node in, and then we're going to connect the other side of the resistor to the node out, and then we're going to give it a value of, in this case, 9 and then units of kilo ohms. So you can just say ohm. There we go. Right. Oh, sorry, I just want to correct that. That should be a capital O. Now it is actually possible to use the ASCII symbol for ohms, so we can use that omega symbol. So we could use kilo ohm. However, some text editors will throw errors. You can see my flakeates crash there. That might actually also be because of the @ symbol. So we're just going to stick with ohm, capital O, for now. And then finally, for our voltage divider, we're going to create another resistor. We're going to call it resistor 2. So you can use a number, or you can use a value, a text value like input. So we're just going to call it resistor 2 in this case. And then we're going to link resistor 2 from the output node, and we're going to link it to the circuit ground. And we're going to give this resistor a value of 1 kilo ohm. Okay. So theoretically, now we should have produced in our spice these various inputs should lead to a netlist being created very similar to a as a voltage divider, which if we bring up an NGSpice GUI model, so I've produced a voltage divider here. We've essentially created a circuit exactly the same as this. It's just we've done it using 3 lines of code as opposed to a drag and drop GUI interpretation. So let's actually try and output that Spice netlist. So before we can spit out the Spice netlist, print the circuit that we've produced, we actually need to create a simulator instance. So let's create a simulator, and we're going to simulate on this circuit which we've been producing. So circuit, and then circuit.simulator, and then we can set a couple of parameters here. The basic parameters will just be temperature. Temperature, and we're just going to set that to 25 degrees, and then the nominal temperature will also set to 25. And you can see here I've actually already got them commented out, so I'm just going to uncomment that. And now what should happen, I'm just going to plot pin and exit. So when I run this code, what should happen now is we print out the circuit netlist. Hold on, let's actually adjust that. We've created a circuit. Now we want to, let's ignore the simulator for a second. We've just created this circuit, and we just want to print out the circuit or netlist which we've produced. So let's do that, shall we? So we're going to Python 3, and this file's called tutorial 2. So we're going to run it, and as you can see, we print out the circuit netlist. I'm going to zoom in a little bit because it might be a bit difficult for you to see. That should be a bit better, hopefully. So we now have the circuit netlist, and we print out, and for those of you that have ever used netlist before, this should be incredibly familiar. So we have the title, which was the name of the circuit we assigned, voltage divider, and we then have the 3 components. And we can go over to our NGSpice, and if we go to Tools, Export Netlist, let's go to View Netlist, Spice Netlist. We can actually see a very similar, not quite exactly the same, but a very similar Spice netlist as the one we've just produced here. So there you go. So you can see we've got, resistor 1, resistor 2, and our voltage source. So very similar indeed, and that's great. What you'll notice on this NGSpice is that we also have some commands. And these commands are introduced by the simulator function that we wrote down. So I'm just going to exit that for now, and we'll go back to the code. So if we now allow this simulator instance to be produced, what we can then do is we can print out the simulator, and what we will find, I'm just going to shove in an exit there. What we will find now when we run it is we have the original circuit netlist as we did before, but now when we print the simulator, we actually print the whole Spice netlist in its entirety, including the commands. So we now have the title, we have the 3 components, we have our options which are now displayed, and then we end it. So that's great. And if we printed the simulator after we added in an analysis, we'd probably also see .op, so an operational analysis. So let's go ahead and actually add in that analysis. So we're going to actually want to run an analysis. So let's create a result called analysis, and then we're going to take the simulator instance we've produced, and then we're going to run a operating point analysis. There you go, operating point. And we could pass in some parameters if we wanted to, but for now we're just going to run the default operating point analysis. So let's run that, and let's now put our exit, and let's just print the result. So we've gone through, we've created a circuit, we've produced a simulating instance by defining some parameters, and then finally we are going to run an operating point analysis, and this will actually run the simulation, and it will produce some results stored in this analysis variable, and then we're going to print out the analysis variable before exiting. So let's do that. So we can see now we've printed out the circuit as before, printed out the simulator as before, and then what we can see is we can see this logging instance telling us that the subprocess, the Spice subprocess has started, and then we've printed out the analysis. However, what we find is actually this analysis value is some kind of dictionary, it's been stored at some particular point. So we want to actually extract the data from that analysis. Now, to do that, we can do a few things. The simplest of which is to, again, I've got this pre-written. We printed the analysis and it pointed us to the position where it's stored. If we know the names of the nodes, we can say, right, well, let's consider node in, and then let's print the float of node in. So, and then we can also print the string of node in. So we're just sort of trying to extract some data, and this is how the data is stored. So I'm going to stop printing out the simulator and circuit, just for a bit of clarification. Okay, so what we find now is, again, the analysis has been stored at a particular place. If we just print a node from the analysis, it prints the node name. If we print a string of that node, it prints the node name once again. So we see that's the default. But if we force it into a float, if we say let's float the node, it will then print the value. And we know, because we set it, we know the voltage at the input is 10 volts. And sure enough, the voltage is 10 volts. So we could do a similar thing with node rather than node out. We could for node in, we could do node out, node out. And what we see is, again, our input is 10 and our output is 1 volt. And if we flip over to NGSpice, if we run this circuit, do an operating point analysis, we find that the input is, of course, 10 volts, which we've set, and the output is 1. So just a simple check there, and we know that our NGSpice is running correctly. So this analysis output is pre-formatted, and you can extract the data in various ways. Something which I like to do is to actually format those outputs myself. So I'm going to copy in a function here. I'm going to copy in a function, put it at the top. Let's just call this functions. So we've got a function here. I'll talk you through it. So a function called format output. What we do is we pass in an analysis. We pass in an analysis value, which we've produced from the simulation. We can give it some information about the simulation. At the moment, we're only using operating points, so don't worry about this. In fact, I'm going to just delete it. So we only pass in the analysis. And what's going to happen is it produces a dictionary which contains those simulation values. So we've got this simresdic, so the simulation results dictionary. We create it, and then we loop through each of the nodes stored in the analysis outputs. We produce a data label, which is the name of the node, and then we create an array from the corresponding node output values, and we assign it to that position. So if we now use this format output analysis function, we can say out dict equals the format output of analysis, and then we can print our out dict. And if we do that, we now have a dictionary of our formatted outputs, which is a bit more, for this purpose, is a bit more visually pleasing, because we can see that our input contains an output array of just 10 volts for the first instance. There is an operating point analysis, so there is only one instance, and then our output has a corresponding voltage value, which in this case has been generated by the simulation as 1 volts. So you can either extract the data directly from the analysis, or do some formatting of your own to produce a slightly different formatted output. Not strictly necessary, but just for this purpose, I wanted to be able to show you how it can be formatted. So hopefully we've covered a couple of things here. We've covered some basic components, a voltage source, a resistor, how you can assign a unit to the values, what the various positions within the definition of the component is, being the name followed by the one node, and then the second node, and then the value. There are many components. If you've used Spice simulators before, you can. There are very many components which can be used, from just standard volt sources, resistors, capacitors, inductors, all that sort of thing. Or people can build. You can build components yourself using subcircuits. So potentially you'll have a component which actually has 3 terminals, not 2. In which case you might have the 3 terminals connected before the value is assigned to it. In this case, 10 volts or however many ohms for a resistor. So you can now start using these components. We can build very simple circuits, and we can start to see how more and more complex circuits could be produced if we wanted them to. We've then looked at the simulator, applying an operating point analysis to our particular circuit, and then finally how we can format our outputs if we want to. So I hope that's helped giving you a little grounding in PySpice and its very basic uses. Thank you very much.